see you. Allegedly. Yeah, that's right. You too, how have you been? I'll let you get ready for the
Christian is there. Sorry, but this is for you.
All right, maybe. Okay, I guess I'll get started. Be a minute early, so give the speaker more time. So yeah, it's my pleasure to welcome you all to the EECS Colloquium today. And it's a privilege to really introduce a speaker who really needs no introduction at all. And he's also asked me to keep it brief, so he has more time for the talk. But let me quickly say that Avi Wigderson is a legend in the field of theoretical computer science. He is the Herbert Maass Professor at the School of Mathematics at the Institute for Advanced Study in Princeton. His wide-ranging work has made seminal contributions to almost all aspects of theoretical CS, complexity theory, algorithms and optimization, role of randomness in computing and cryptography, parallel and distributed computation, pseudo-randomness, combinatorics, graph theory, you name it. Avi has made great contributions. And as a theorist, he has won perhaps the three biggest awards a theoretical computer scientist can dream of, which is the Nevelina Prize, the Knuth Prize, and recently last year, the Turing Award, like the Nobel Prize for computing. And as if that is not enough, he is also a winner of the Abel Prize, kind of the Nobel Prize for mathematics. And so it's an incredible honor to have Avi speak today. And I'll also mention that beyond all his distinguished thing, one of the amazing things is he's extremely approachable, and his legacy touches so many postdocs who have gone through his group at the IAS in Princeton. And so it's a real pleasure to introduce Avi. And he will tell us today about Alan Turing's works.
Yeah, thanks, Venkat. Thanks, everybody, for coming. It's always a pleasure to be here. What I want to tell you about today is, Alan Turing. In computer scientists, you go through this education, and of course you learn about Alan Turing's paper on the Turing machine, and then I thought I knew what I should about him. I read a couple of more papers about his AI paper and so on, and then Turing mentioned, Venkat mentioned I got this Turing Award, and I thought I should do justice to my knowledge of Alan Turing, and I spent a couple of months just reading almost everything he wrote. And I just want to tell you about this experience. So I'm not going to talk about his life, a very short life with a tragic end that I'm sure you all know. I want to talk only about his work. This is more or less his academic CV, where he spent time during his career. And I'll more or less tell you about one paper from each period. I could have given a 3-hour talk, a 5-hour talk, but I'll restrict this to a 1-hour talk. There are plenty of stuff I'm not going to mention. I'm not going to mention any practical work, and he did a lot. Of course, he built computers, and he wrote about building computers. He programmed a lot, and he wrote about the practice of programming when there were no computers and people just started doing this. As an undergrad, he proved one of the most general forms of the central limit theorem, and I'm not going to tell you about this. He wrote a seminal paper on numerical analysis where he defined condition number. He did it, yes, and he devised what we call LU decomposition. I'm not going to talk about this. He worked, of course, on encryption. He was obsessed with teaching for computers to play chess, and he was even more obsessed with trying to refute the Riemann hypothesis by trying to find the zero outside the critical line. And we will not talk about this. You can ask me at the end if you want. So I want to start by the paper you all know, but I want to, so about this paper I'll talk about it, and I'll talk about things I thought and some work that we in the field did following it or inspired by it or things you would have loved to know, I think. So this is a famous paper on computable numbers with application to the Childhood's problem. Easily the most impactful math paper ever written. He did it when he was a fellow in Cambridge. He was just finishing his undergrad, but this was like a postdoc, if you will, on the strength of this central limit theorem he put. So you all know what's in this paper. The way he got to this question is he took Max Newman's course, a topologist interested in the foundations, and who told them about Hilbert's dream, the famous dream, on the foundations that everything true in mathematics is provable, and that everything provable can be obtained, the proof can be obtained by a decision procedure. This dream was famously shattered completely, first Gödel by the incompleteness theorem, and then Turing in his undecidability theorem. He wrote it up and gave it to Max Newman, who looked at this and says, just a few weeks ago I got a paper from Alonzo Church in Princeton who proves the same theorem, undecidability. But nevertheless, as a good mentor, and Max Newman was a mentor to Turing all his life, really, he did two things. The first was write to the editor of the London Mass Society saying, yes, this result is known, was proven already, but that's a completely different proof. A fundamental paper of a fundamental result, you must publish it, and it was. And the second thing he says, look, you shouldn't be in Cambridge, you should be in Princeton, where everybody is working on these computability issues, and wrote Alonzo Church to ask him to take him as a graduate student, and he did indeed went there. We'll talk about that next period soon. So, what's so fundamental? Well, in order to shatter Hilbert's dream, you need a formal model of what computation is. It didn't exist. It didn't exist. You somehow need to define a notion that captures everything that anything might possibly compute. That was the question, and of course people were occupied by this because of Hilbert. Gödel has his definition, Church has his own definition, and Turing came up with what we are familiar with, completely different than them, this very elementary primitive device, which we today call a Turing machine, suggesting that this is it, this is computation. Now, Gödel and Church saw this and immediately agreed. They said Turing's definition is the right model. In fact, the name Turing machine was coined by Church. And what do you need to do when you introduce such a, a formal definition of such a vast notion. You need to argue that this is it. It captures everything possibly computable. This is what we call today Turing thesis. And the way Turing argues this, and this is common to all his papers, is with beautiful eloquence and generality. He gives three different types of arguments, why this is it, why it captures everything possible. Well, first he wants to say, this emulates human computers. Now, you may not know this, especially the young ones, that a computer was a job description in these days, mainly of women who did calculation. That was what was called computer. He shows how, and this in fact inspired him, how what we do when we compute is doable on his machine. Then he shows that a large bunch of things that you might want to compute, like the digits of pi and e and various other constant Bessel functions and so on, he gives programs to compute them on his device. And finally, the third type of argument is that this is equivalent to other notions proposed. In fact, it's two notions. Once he realized that Church wrote this paper and he found out about this, he did lots of things without knowing about the background. So when he realized this, he shows that in power this is equivalent to lambda calculus and to recursive functions. Now, this was the birth of a theory of computation. Why? Because it's a mathematical model. Once you have a mathematical model, you can do math with computation. But actually, it is far more than that. Because the model is so simple and gives you an exact meaning to a unit of time, an exact meaning to a unit of space, you can start quantify the resources allocated by different algorithms, and in fact soon after, or not soon, a few decades after, Hartmann and Stearns took it up and defined these complexity classes, and from these two we have now, I don't know, 1,000 different ones. We have a complexity zoo of complexity classes. We quantify all sorts of resources in all sorts of limitations. Now, what's the theorem being proved? The theorem is that there is this problem, mathematical problem, the halting problem that cannot be solved by a computer. In layman's terms, it says that debugging programs is impossible to solve by computers. I love the way Christos Papadimitriou talks about it. He says that computer science as a field was born aware of its limitations. Not everything can be done by computers. In fact, the most basic problem in computer science cannot be done. And he says that's unlike, let's say, physics, where it took them centuries or millennia to discover limitations like the uncertainty principle or the second law of thermodynamics. This is a huge impact on mathematics, because now you have the mathematical standard to judge whether certain mathematical problems are understandable by humans or not. Namely, we can compute the objects relevant to these fields. He initiated this in his work on the word problem in semigroups, and then others, Novikov and others proved the same for word problem in group. Basic problems in mathematics cannot be solved by computers, so that in particular there can be no complete theory explaining them, characterizing them. And much later, it took many years to prove that basic problems in number theory, like solving polynomial equations in integers, cannot be done by computers. And all of these are done by reductions to the halting problem. So they are done by designing algorithms. And of course, there are algorithms also in the positive side. People try to prove that other central structures in mathematics can be understood algorithmically. Tarski did it for the first order theory of the reals. Haken did it for in topology, for nothingness. And I should stress that the algorithmic point of view entering math resulted in lots of new structural understanding. The techniques developed, like quantifier elimination and normal surfaces for these algorithms, are fundamental for the theory, not only for algorithms. Now, how did he prove it? We all know how he proved it. He designed, first of all, in the paper, the universal Turing machine, namely a machine that can simulate other machines, and realizing the programs that data are the same thing. You can run machines on the universal machine, and therefore you can simulate them, and then you can diagonalize against them, as we all know the proof, I'm sure. And this proof technique became a major proof technique for the field, simulation and diagonalization. This is a way that we first proved results in computational complexity. In the same paper, Maass showed that more time buys you more computation power, more space buys you more computation power, exactly using his technique. And I want to stress, he says that this simulation of Turing machines by universal Turing machines is an efficient procedure. That's the reason you can even have this quantization. This was taken to more elaborate forms of this, so it was such hierarchies were put for non-deterministic machines, and I'm not sure how many people, this is not taught anymore. The previous tempi was already solved if you care about linear time rather than polynomial time. So we know using Turing's technique, even results like non-determinism is more powerful than determinism in linear time. Turing, you might wonder, and so lots of things I didn't know. Where does non-determinism come from as the basic notion in the field? And the way you learn, I learned it, and many others, is that there is a famous Rabin-Scott paper on automata, and they defined this notion. But actually, if you look at Turing's paper, he tells you in this paper that towards the paper is going to talk about automatic machines. These are machines where every move is determined uniquely by the current configuration. But he says that it's also interesting, I will not discuss it here, to consider choice machines. What are choice machines? The next state is not fully specified by the configuration. And then some external agent must tell you what to do. So he defines non-deterministic machine explicitly, and moreover, he tells you why he defines it. He defines it in order to discuss axiomatic systems, in order to discuss proof systems. So here he's talking about proofs, here he's talking about computation, telling us that the contrast between the two is something central and worthy of study, and he was interested in it in particular. In fact, you might view his results as a separation between proofs and computations, because recursive sets are what's provable by, computable by finite algorithms, and RE, recursively enumerable, are those sets provable to finite algorithms, or verified by finite algorithms. So he proves that the two are the same by the halting problem. And what we are, major motivating force of our field is the analog for efficient algorithms, let's say polynomial time algorithms. The first paper defining NP, Cook's paper, famous paper, is actually borrowing from Turing. The title is actually the complexity of theorem proving procedures. Of course, one thing I believe Turing would have loved to see is how far we have taken this contrast between proofs and computations, what kind of different notions of proof systems we invented in the field since his paper. You are all, maybe many of you are not familiar with all these acronyms. Each represents a different type of proof system, and these are characterizations. We understand fully, except for P-Centy, the power of this very important and different proof system. Okay, so this was about the first paper. It's a paper that after you write one, you don't need to do anything. Of course, he continued. He moved to Princeton, as I told you, and he wanted to work with chairs. There were many other people doing computability issues, although he didn't talk to many. He didn't like Princeton. But he wrote a thesis there. He was a graduate student. I was there 2 years, wrote a thesis called Systems of Logic Based on Ordinals. And I'll tell you one thing from this thesis that I'm sure many of you are familiar with. He invented another fundamental notion that we are living with and playing with all the time. This is the notion of an oracle. So he suggests, let's suppose we are supplied with some unspecified means of solving some number theoretic problem, mainly a decision problem, and a kind of oracle, as it were. So he is even inventing the name for it. And let's study this. The reason he was looking at this is to see whether undecidability is the end of the story. Suppose you can solve undecidability. Can you solve then every other problem? And yeah. This had, so we denote it usually with the superscript. This is a machine with an oracle O. In general, you can take a class of machine with oracles from another class. This had a huge impact on recursion theory. People define generalizations of these basic classes R and RE, a whole hierarchy called the arithmetic hierarchy, and proved that they are all distinct. This proof is, of course, again using Turing's technique of simulation and diagonalization. In the theory, in the complexity theory, the analog or polynomial time analog of these classes were also defined as the polynomial time hierarchy, but here we don't have any separation. We don't know that any of these two classes are different. So they are defined by oracles, but oracles come in another surprising way as an excuse for understanding why we cannot prove this. So why is it that I told you about this time hierarchy, this technique of Turing simulation diagonalization works? Why can't we use it to prove P different than NP or any separation? This came in the brilliant paper of Baker, Ginn, Solovay, who said, look, this technique is oblivious to oracles. If we prove something for Turing machines without oracles, you prove the same thing if you add the same oracle. And that's one property of the technique. On the other hand, they supplied oracles which can either separate or make equal P and NP. In other words, if a question has this property that can be yes or no with different oracles, this technique will not work. So oracles supply the excuse, and this led the field into this, I guess, contemplative state of mind where you inspect your own introspective, inspect your limitation. When you cannot do something, try to explain it. That we call barrier results. So this was the first barrier results, and there are many others in the field. They usually not only supply excuses, but maybe provide ways to go around the excuses, and sometimes we can bypass barriers. So oracles, they are absolutely fundamental. Okay, let me move to the next stage of his life. The war broke out, 1939, and he has taken a code-breaking course the previous year, and he enlisted in Bletchley Park, Hut 8, the famous Hut 8, to work on breaking the Enigma code, in particular the naval Enigma code of the Nazis. So I'm sure you all know the story. After the Nazis took over Europe, England was isolated and was totally dependent on supplies from the US, both food, ammunition, weapons, everything. So there were convoys of ships going from the US to England with all these things, and the Atlantic was infested with U-boats. There were maybe 60, 70 in the beginning of the war. There were 400 at the end of the war, and they were sinking you know, these convoy ships right and left was a real major thing. The cracking of the Enigma was, by Turing and his friends, was declared by Churchill to be the greatest contribution to victory in World War II, no less. So people know this story, and they know that you know, you can represent it as a competition between two machines, the Enigma machine and the bomb, this kind of device that was searching through keys very fast, the keys to the Enigma machine, very quickly, and that's usually how the story is told. And that's how I knew it, but like a certain, you know, fight between these two machines. But what I didn't realize is how much theory went into this. And I must say that it's sort of shocking to think, I'll show you what theory I'm talking about, but surprising to think that Turing had the presence of mind during this extremely pressurous time where, you know, these ships were sinking, to, you know, in order to enhance this process of searching for the right key, to go and do math, because this would be foundational to improving the efficiency. So I'll tell you about his work in these areas of probability and statistics and information theory in the field, and I would like to put papers of Turing, but there are none. He wrote several, you know, lecture notes and various notes, but he never published them. Of course, most remained secret till the 90s, but luckily John Good, who worked with him in Hut 8, wrote papers on this, so I'll tell you about these. Two notions, weight of evidence and population frequencies. I'll be brief, and maybe you will not understand everything there, but that's not important. I want to stress a theory. So, Good, just to make sure that it's Turing work, Good himself tells you it is. About the second notion, he tells you the formula 2, I'll show you in the next slide, was suggested to me by Turing. He showed it to me, he showed me the proof, he showed me, you know, he deserves full credit for this paper, but he allowed me to publish it. He also, on the first notion of weight of evidence, Good wrote a survey at the end of the year. There's a whole theory there, and he says this theorem was suggested by Turing, and the other one was suggested, and so on. So Turing was the leader of this project. Let me tell you briefly about these two notions. What are population frequencies? This is the most basic problem in statistics. You have a sample of n items, ILD samples from some distribution unknown on some alphabet. Okay, so you, and you ask, suppose you look at a particular item which appears k times in the sample. What probability do you believe it has in the distribution? And you would all say, and I would say k over n, of course, end of story, but that's not the answer. It's not the answer because it's not the type of situation that we are normally thinking about. This is more like you walk in the forest and you see two zebras, one giraffe and one lion, and I ask you what's the probability of a lion. You wouldn't say a quarter. There are all these animals you didn't see at all. So this is the situation here. The sigma, the alphabet, is all the German words, right? It's much larger. The alphabet is far larger than the sample size. So what do you do? Here's what you do. This is called today the good Turing test, which Good says that Turing shows him. Suppose that n sub k is the number of times you see items k times exactly. Then you do this. Don't try to digest it, although it makes sense to do afterwards. It's really ingenious. It's not k over n, it's k plus 1 over n, but you taper it down by n sub k plus 1 over n sub k. It's really, it's sort of magical, and there are examples you can do. But let's not go there. I just want to say that we know that this is, they all knew that it should be smooth also. It's smooth, it's a smooth version. It took many years to show that this is the best you can do. The formula, smooth formula. is the best you can do. For any distribution, this will give you as close as estimate as can be hoped for. This is just one example, connections of TCS and statistics are now abound, and this is another field which started by Turing. The other notion is another thing you are extremely familiar with, another basic question. There are two distributions, P and Q, and I give you a sample from P. How much do you learn to, how much more convinced are you that the underlying distribution is P given this one sample? And, how do you quantify this? And Turing suggests to study this random variable, log P of X over Q of X. This is in early 40s, right? He suggests to study this random variable. Of course, we all know this expectation of this random variable. We call it scale divergence, Kullback-Leibler divergence, but it was there already, and they do much more than study the expectation. They study higher moments. They have a bunch of beautiful theorems. Some of them were later discovered independently when Wald developed sequential analysis. Sequential analysis is simply statistics where the sample size is not fixed in advance, but you learn more and more. This is what they need to learn as they were gathering information from breaking messages by Enigma. All right, we are done. So we are switching context very quickly. I have two more papers to discuss, so that's okay. I hope you get a sense of the immense variety that, of things that Turing considered. And here we move to his famous paper on AI. After the war, he went to London to build the ACE computer for the government. He was very unhappy there. They didn't let him do what he wanted to. And then Max Newman, same one, called him to Manchester, where he was building another computer, the Manchester Baby. I want to stress, it's pretty amazing. Already in 1953, there was a position called Reader of the Theory of Computation. A reader, this is England, right? Professor of the Theory of Computation. Turing was given this position with a huge salary boost, so they valued theory. And during this period, he wrote the paper, Computing Machinery and Intelligence. He wrote a lot about this, not just this paper, as I'm sure some of you know. And I want to talk a little bit about this, because there are things in this paper that you won't know. You know about the imitation game, I'll get there, but there are plenty more that maybe you didn't realize were there. And lots of the things that are there mainly because Turing, like in many papers, not only set up notions and fundamental notions, but already wants to argue why his notions are the right ones or important ones, and he prepares for arguments from other scientists. In this case, he got lots of arguments. There were many debates he held with other people, other scientists in different fields, both in writing and on the BBC radio. So he prepares a bunch of arguments. This leads him to say things that, are not about intelligence, are absolutely fundamental for us. First thing is, he introduces, again, you wonder who introduced first formally probabilistic algorithms. This is Turing in this paper. He suggests, another type of machine you can consider is Turing machine with a random element. So flip coins for some of your moves. He suggests it, he suggests how to do it, and he suggests in other places other means, physical means of generating random numbers. So probabilistic machines are defined in this paper. Moreover, pseudo-randomness is already explored in this paper. By the way, probabilistic algorithms are defined because he wants to convince audiences that machines don't have to be predictable. People say machines will never have intelligence, they are always predictable. So they are not. But he also, once randomness is in, he wants to understand pseudo-randomness. So the first thing he says is that it is not normally possible to determine from observing a machine whether it is using randomness or not. Because how do you tell if this is it, or maybe it is just using in some way the digits of pi. But even more fundamentally, he makes a formal definition of a pseudo-random generator, or pseudo-random function generator. This is quoted in the famous paper of Goldratt, Goldwasser, and Micali, where they formally define this notion. And they quote him. He says exactly what they say. He gives their definition. I've set up on the Manchester computer a small program using only 1,000 units of storage, whereby a machine is supplied with 116 figure number and outputs another 16-digit number. I will defy anyone to predict the value of this function, of this program, on any unseen input. So that's basically the definition of pseudo-random functions, if you throw in polynomial time and blah, 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 whatever we need. But that basically is the definition. So he already sees or gets right the definition that we are all using in cryptography. That's about randomness and pseudo-randomness. Now, he talks, of course, about machine learning and machine education. And I want to stress, I mean, in many of these papers, you really have to think, I mean, we are born into this computer age. You have to think there are no computers, basically. No computers. And the computers that were people started building after the war had mostly one purpose, clearly military purpose. Trajectories of missiles and stuff like that. Also, IBM were developing computers for business purposes, but Turing seemed to have been the only one to think immediately that if these machines exist, they may think like us. And he's advocating this point of view. That's the purpose of his paper, completely against the current of activity. He did many things, he says many things in this. He was very obsessed with analogies with the brain. He wanted to know, he believed that intelligence in particular depends on how much memory you can have in a computer, and he was asking his biologist friends about sizes of human and other brains. And he argues, that's another argument he needs to give about people, arguing that how can machine learn? And he tells them, a machine learns because the machine the argument was, it's fully prescribed, it has a program. He says, sure, but, program can change itself and it becomes a new program. So all sorts of things we take for granted today, he first puts it down on paper. He argues very forcefully that, against the complaint that machines might err. You expect machines to be fault-proof. Like you go into a car, you don't want it to break down or turn left when you move the wheel to the right. But he says that if you want it to be if you want an intelligent machine, you must allow it to err. That's what we allow ourselves, and we must allow machines to do that. He talks about the education of machines, and he says, well, like child learning, we are born with some initial state of mind or initial program in the machine, but then there are two kinds, and he distinguishes them, of sources of learning. One is experience from whatever the environment is doing, but the other is education. So we should teach the machine like we teach children. It was interesting, during the time I was reading this, I got Valiant's new book on educability, and where he mentions, of course, the statement by Turing, and says that in the history of machine learning, of course, now everything changed, but people didn't talk much about education. And I was thinking to myself that in general, in these comments Turing made. He would have loved to read this book or the book about pack learning, where errors are fundamental, or the book about circuits of the mind, where the analogies to the brain. This is only Valiant's work. There are many, of course, huge literature that, and works that he would have loved to know about. Finally, I'm getting to his main point, his definition of intelligence. And it's, again, his prose is beautiful, and it's a pleasure to read. He starts the paper by saying, you know, how do you study the question, can machines think? He says, well, you can do what philosophers have always done. You define these notions, what is a machine, what is it to think, and yeah, we start discussing this, but he said immediately we run into problems because you will not agree with my definition. And we start arguing about the definition. And he says instead, we should just test it. So he's rejecting the objective philosophical point of view of defining this, because definitions, they may not be testable, falsifiable, they do not have a universal meaning. We still argue about them. And instead of that, he's suggesting subjective behavioral definition that, of course, you know and we'll go through. These may be, you know, precise, testable, operational, useful, and, as we shall see, revolutionary. So let me first tell you what I'm sure you know, the famous imitation game. This is his way of testing whether a robot or a program are, you know, intelligent or can converse with humans. Of course, in today's chatbot world, the issue is not whether it can be done, but just the definition itself, the imitation game. He sets up two parallel worlds in which a referee, and you allow many referees, the referee interacts with one of them, doesn't know with whom, and the end should say, you know, I believe this is a machine, or just give a confidence roll, give a number between 0 and 1. And the way you would define intelligence is, you know, that the robot is intelligence if in these two worlds, the referee, any human referee in Turing's definition, cannot distinguish the two. The two numbers are very close to each other. So that's his paradigm. So his paradigm, you know, I want to tell you about how we in theoretical computer science use this paradigm. Paradigm is the two things are the same if they cannot be told apart. Very simply. By what? By a reasonable test, reasonable to the task at hand. So this, I want to demonstrate the power of this paradigm in current ECS, which has amazing impact on everything. I'll give 3 examples very briefly from crypto, from pseudo-randomness, and from privacy that I'm sure many of you have seen. Fundamental definitions in which the imitation game paradigm is used. And just to comment, which is, I guess, it's sort of obvious but has to be repeated, especially to students, I think, is that, well, our field, I think, is primarily a definitional field, and mathematics as well. And when you have the right definitions, the right notions, this is the primary objective. Once you have this, often, you know, the right theorems, theories, constructions follow. So we'll see some definitions using the imitation game. In cryptography, what's the basic problem? The basic problem is you get some encryption function. What do you want to know? Whether it's secure, right? Protect the messages. So what is secure? Here is the famous Goldwasser-Mikali definition of secure, semantic security. It's done by an imitation game. So set up an imitation game between what? The encryption of 2 different machines, 2 different messages, any 2, M0 and M1. You let the encryption encrypt them, and then you send it to an arbitrary adversary. The only limitation is that this adversary is efficient, and it should tell whether it's M0 or M1. And if the output of this machine, any such machine, is very close, and it's close regardless of which 2 messages you encrypt, then you call it the encryption function secure. This is a definition universally used in cryptography. This definition tells you immediately that encryption, secure encryption must be probabilistic. Deterministic function will never pass this test. And of course, we have a way of making this definition real under various assumptions. This is true not just for encryption, but any cryptographic protocol. How do you prove or how do you argue the security of a given protocol, let's say, which runs on the internet? You want to say that some set of players, maybe with bad players, part of them cannot get any more information than they should. You set up an imitation game. What is this imitating against? You dream up an ideal world, and a world, let's say, where there is a trusted party, which I called here the government, where you have the protocol that everybody sends their information to this trusted party, and you get back, everybody gets back what they should. If for every set of players, this is the definition, every set of players, the communication it sees is indistinguishable in these two different worlds, then this protocol is secure, because it cannot be distinguished from protocol played in the ideal situation. So this is key in cryptography. In a study of randomness, this is critical. How do we say that a distribution, when do we say that a distribution is pseudo-random? Again, we run an imitation game against the uniform distribution, which is the paradigm of perfect randomness. And if no efficient algorithm can tell apart these two, then you call it as random as the uniform distribution. Finally, the last example, I'm running through them quickly, but I'm sure they are known. Privacy, the basic question is there's a database, you want to know whether it's safe for you to participate in this data of records of many people. And the idea of filtering answers to queries using nodes is, half a century old, but there was no formal definition of when you say that this is private and how private it is, such a mechanism, until this famous two papers about a decade ago, about 2 decades ago, I should say, we said that such a filtering mechanism is private if whenever you take two databases, arbitrary two databases that differ only in one position, adjacent databases. Let's say they differ on my name. If whatever query is being asked and gets an answer using this filtering mechanism, no algorithm can, all these queries cannot distinguish, they behave the same on the two databases, then I'm happy to participate because clearly nothing is learned about me in particular. So again, the imitation game serves as a bed for the definition of a fundamental notion. Okay, so I have 5 minutes for my last paper, and this is a paper you all see in Manchester. It's about morphogenesis. He wrote a paper called The Chemical Basis of Morphogenesis. Now, I don't know if you knew that he did biology. He not just wrote a paper on biology. This is one of the most quoted papers in biology ever. Okay, it's not just an arbitrary paper. It has 20,000 references. And I want to tell you in a couple of slides what's in this paper. So this is totally different than anything else is done. So what's the problem of morphogenesis? It's one of the most fundamental problems in biology. And here is the problem. I mean, I'm sure you see the problem, right? What's going on? We all start, all mammals start from the same kind of starting point, a homogeneous fertilized egg, something totally symmetric. How did it get to be this zebra? I mean, what explains the stripes, or forget the stripes, what explains the head, the tail, the legs, the body direction, all these things change from this little ball. And it didn't just change. I mean, all zebras look alike, right? It changes in a predictable way. There's not just that asymmetry happens. This may happen randomly. It's the same asymmetry, structural asymmetry, it's persistent. How does it happen? So I don't know about you. I mean, I look at this kind of problem, even though I read the paper. I read this kind of problem, I throw my hands up and I move to an easier one, like P versus NP or something. Yeah, what do you do? What do you do? And it's amazing. I mean, like in the computability paper, he put his finger on a really simple, very, very simple, elegant model explaining this. And this is one of the, we use the main explanations we have for morphogenesis. I want to tell you the model. So here's again, he writes beautifully. It says, in the section, a mathematical model of the growing embryo will be described. So no less. I'm going to describe the development of an embryo in the womb. The model will be a simplification and idealization and consequently a falsification. It is to be hoped that the features retained for discussion are those of greatest importance in the present state of knowledge. Okay, so I don't know a better introduction of a student in the sciences to what the scientific method is than this paragraph. Anyway, here is the embryo, a ring of cells. So he's suggesting a model he calls reaction diffusion model. It's a chemical model. And he simplifies the embryo to be a ring of cells. He studies both the discrete and continuous one. I should stress this is a mathematical paper. There's plenty of Fourier analysis and spherical harmonics, but he writes it both to a biological audience and a mathematical one, and he takes a lot of patience in having simple examples in order to demonstrate the general results. What's the model like? The state of the system is the quantities of morphogens in each cell. So morphogens is the chemicals. So you have chemicals A, B, let's say, you know how many there are in each cell, that's the state of the system. And the model says that you alternate two parts, you repeat alternating two kinds of things. One is a chemical reaction between the chemicals in each cell independently, and then diffusion between neighboring cells to get equilibrium of the quantities. And they happen in some given rate. That's the information. And initially, it's a completely symmetric situation, okay? They each have the same quantity of A and of B. And transition is this alternation, as I said. And the point is that, they have the same quantities, but we are in life, you cannot have the same number of molecules exactly of A and B. This situation happens to be, in some cases, unstable. So it's an equilibrium, but it's not a stable equilibrium. Tiny, tiny changes will start something happening. And then he analyzes this mathematically, and he shows how symmetry breaks, and not just how symmetry breaks, but how structure emerges that has a particular form. It can be, periodic structure, or you have, moving structure. He analyzes all possible structures that emerges in some of these cases. There are several things to stress, but in particular, it's clear that he was thinking about what we are doing a lot with many other sciences today. This is a computational model. He stresses that the stage next step follows deterministically from the current state, and basically a computational model. And then the last slide I have is that tell you what he analyzes, what he studied. So first I want to say this is, nothing less than cellular automata, right? The model that we believe was invented by von Neumann and Ulam. He already has it, the various forms of cellular automata. The first one, so he studied a two-dimensional ring of cells, as I told you. He studied it in order to explain what's called phenotaxis, like the placement of leaves around the stem, or more, what really intrigued him is this hydra. It's sort of a sea creature that if you cut it in the stem, then you see a ring of cells. And he said, now these tentacles will grow, but they will not grow out of every cell in the circle. They will grow out of some of them. There will be 5 or 6. Why? How does it happen, even though it's all symmetric? So this paper explains this. He really goes for the embryo. In a three-dimensional model, he's trying to explain the, people with kids will know it better than people without kids. You may know that in the first 2 weeks, the fetus is in a blastula stage where, the cell is dividing, but still looks like a ball of cells. And then in the 3rd week, something happened, the direction is formed, really the spine is formed, moves to the gastrulation, to the gastrula phase. And he does the analysis of the three-dimensional case, and he predicts and shows how gastrulation arises. And he also studied this planar grid in order to understand dappling, these patches of color. And here he doesn't mathematically analyze it, but he actually just runs simulations on the Manchester machine. He had every Sunday night and every Thursday night the computer was his, and he was working all night programming and simulating and doing also chess and Riemann hypothesis. But, okay, so as I mentioned, we do lots of following in interaction with, almost all sciences. So, summarizing, it's just beautiful. It's hard to describe. So it's obvious. I'll say some obvious things. What a great thinker he was, and the impact he managed to have. You get a sense from reading different things that he was, at the same time, clearly you saw a scientist and a mathematician, maybe most, basically, but he had a very strong philosophical bent and was interested in, sort of higher level issues. But you also, when you read his work on computers and on programming, you understand what a hacker he was. I mean, he was interested in electromechanical properties of all the devices that he needed for these early computers, and he was an avid programmer, very diverse. He contemplated things he considered fundamental, and he seemed to have been totally fearless. I told you when discussing the war that he understood that theoretical understanding is primary to implementation. You will be much better off if you first have a theory. He was very critical, very judgmental, and he was brutally honest. You see this in the artificial intelligence paper. It's really interesting that I told you he prepares responses to various objections about intelligence of machines, but he also evaluates his responses. He says, in this case, let's say the theological objection, my argument shatters the... But on another issue, another kind of objection, I have this response, it's not so strong. I'd better improve it. So he's critical on himself. Yeah, his clarity of thinking is just amazing, and also the clarity of his writing. And I think Einstein said that models should be as simple as possible, but not simpler. And I think, his model certainly fit the bill. And he wrote very few papers, and he wrote them only after he was completely, he exhausted what he knew. Okay, that's my favorite last slide. Anybody wanting to read not about papers by Turing, but about complexity theory, and doesn't know, I heard the conversation years before the talk of someone coming from a very different area, maybe literature. Anyway, that's an invitation to my feet. Thank you.
Thanks, Avi, for the inspiring distillation of Turing's legacy. We have time for a couple of questions. I know people next year's at the
Yeah, let them leave and then.
Yeah, my good.
Yeah, so Avi, in your reading of Turing, did you encounter any non-trivial interaction with quantum mechanics?
No.
Short answer, short answer.
Is there a longer question? Yeah.
Thank you so much for the awesome talk. When you were talking about like the use of the imitation game in some of the cryptography groups, you note that sorry, the definition. We talk about how the definition makes sure that only like a non-deterministic procedure would be able to satisfy them.
No. There was no non-determinism.
No.
The imitation game.
Oh, sorry.
No, it's just that, you know, encryption is good if normally no efficient procedure can play a part in encryption of two different countries.
Okay.
Yeah.
That makes sense. Sorry, I guess
The natural definition is still following. What's more surprising is that you can actually meet it, let's say, in the past.
that makes sense. And you think for the case of the original imitation game, again, there's nothing about deterministic processes.
No, it's also deterministic, but there it's very informal. You see, Turing's definition was, of imitation game was not a formal one. It's talking about people. It's not a mathematical notion.
Right.
And we also know at the end of the story, living in the last couple of years, we know that passing in the imitation game is not a big deal. But anyway, what was important to me was this paradigm of an imitation game as a template for many definitions of this.
Thank you so much.
So when Turing kommt, das ist gut? No? Okay. So when Turing wrote his paper about randomness in computation, did he refer back to his non-deterministic machines? Because that seems obvious. But there would be an obvious connection to put randomness at the non-deterministic points.
Absolutely. No, but it could be. He writes about probabilistic machines in the paper on intelligence, and as I mentioned, he talks about it mainly to argue that machines can be unpredictable. Because people, in their arguments with him about intelligence, that machines are always predictable and they cannot be predictable. So he pointed out that they don't have to be predictable, they can do it randomly. It was but yeah, we could have, but didn't discuss it.
Take one more question.
Thanks for the talk. You mentioned that in 1930s, Gödel, Turing, and Church each came up with their own version of model of computation. So why did Gödel and Church think that Turing's model is more, is better?
For the obvious reason, it looks like computation. If you look at the lambda calculus, it is defining functions, right? But it doesn't look like it's doing addition or multiplication, right? It's not, same with the counting functions, they do it, but it's not like natural. They saw a natural, machine that computes. I mean, it's opposite, but yeah, they adopted it immediately. I mean, the
Yeah, the first line of Turing's paper, I don't have it in front of me, so I can't quote it exactly, but he says, where he's developing the Turing machine in that paper, he says, the very first sentence, he's very interested in computable real numbers. And that's the motivation for what he's doing, but he's not going to talk about it in this paper. He'll do it at other times. Now, his definition at the beginning is one that other people picked up later, people like Marianne Porel, called computable and real analysis. I think it's recursive analysis, where they talk about real computation over this numbers that you can actually generate, let's say with Oracle. And he never ever talks about it ever again. The only time he talks about real computation is a paper that you didn't talk about. It's his 48 paper where he talks about what you call numerical analysis, where he actually does talk about computing over the real numbers, and he explicitly does not talk about his original paper. He talks about, let's assume we have a real number A and a real number B, and we can add them together. Let's assume we have an A and a B, and we can multiply them together. Let's look at matrices. And actually, so when he comes back to real computation, he totally discards his initial sentence in that most important paper.
I agree, but I think that what he means in the original paper on the computable number, even though he said it, I remember this sentence, he really means Buddha or integer sum. Even though he's talking about this, he's talking about computing reals, but for him the reals are the digits of the real number, so he said that, this is the answer to question asked in the time. It's one way to define a function, a discrete function. It just lists it as the real number. What's the idea that the output going to time? That's really how it reads, real numbers in this operator. Just a discrete function that you may want to compute a larger input. Of course, you can, if it doesn't justify, you can think of it as a approximation function. But I think that, like you say, in the numerical analysis paper, he really cares about real numbers and errors in basic operation on real numbers like eigenvalues.
And his notion of condition there is exactly the correct notion to convert a real computation to discrete computation. And that's that is in fact the importance of that paper. We'll talk about it.
It's another maybe paper I didn't have.
All right. So, okay, maybe one more question, and then
maybe this is a little bit of a speculative question, but if Turing had had another 10 or 30 years of professional mathematical life, what directions might he have been pursued? Or maybe, and the very, very concrete version of that is, did he have students?
No, he didn't have students. He hardly had collaborators. He was working on his own. And, I don't think he was an easy person to maybe work with. Certainly, some of his projects, practical projects, suffered. But anyway, he had no. In a hard age was the closest that he got to collaborating with people. And so John Dewey in particular, there were several others that worked together on this information field problem. I have no idea what he would have worked on as he lived longer, given the variety of things he talked about. But I'm pretty sure he would continue to be obsessed with teaching computers with artificial intelligence, and probably with the Riemann hypothesis, where he really wanted to do school. Till today, algorithms for computing zeros of the delta function use ideas of school.
thank you very much, Avi, again. Yeah.
one is like, you mentioned that.
At least the question and answer.
Oh, well,
was in
okay.
San Francisco.
Yeah. Yeah, I think it's recorded.
I'm sorry, it's recorded.
It's recorded because I gave
Mass.
it depends.
Great movie. It's better the second time. I enjoyed it.
Yeah, you heard it you heard it the first
I
time.
think the first time.
Yeah, before I gave it as a Turing lecture. Yeah. Yeah.
Do you want? Can you just walk back with
I will work with them. Yeah, I work with them.
How long are you around?
We are here till Friday.
Okay, do you want to meet tomorrow or the after?
We have some plans. Send me email.
Okay, I'll send you email. Okay, I have to go pick up Veer now. But,
Yeah.
good to see
Okay,
you.
yeah, good to see you. Yeah, I was wondering if I see you.
Yeah.
Now you're here. Yeah, great. Okay.
So the first question is like, for Turing tests or those kind of security research you do.
515 and
Yeah.
So like, does that mean like if people do safety research, they usually need to evaluate their approach against some efficient algorithm or some attack?
No, it's just a definition. It's just a definition.
Okay.
And now people design encryption schemes and you want to test them against this definition. So, as you probably know, most encryption schemes are based on some mathematical assumptions, like that factoring integers is difficult. So what you need to prove that meets this definition, you say, if there was some efficient procedure distinguishing two messages, then you could break factoring.
Oh, I see.
Okay,
So we
and
don't really have an attack model.
No, it's just a reduction. The definition allows you to perform such a reduction to saying if it violates the definition, it will violate an assumption that's very clean and easy to understand. That's how it works.
And the other thing is like, how do we know the P is close enough to say secure? How do people claim that approximate equal?
Yeah, so this is the reduction. They say if there's a non-negligible difference between P0 and P1, then you could break factoring.
But how do they show, like for example, they use one way, they get one P?
No, they don't use. They just say, hypothetically, suppose my crypto system could be broken. Broken means the definition could be broken. Namely, I have an algorithm, obviously efficient, that can say whether it's M0 or M1 with advantage with a gap of, let's say, 1 over n.
Okay.
Okay, so the messages are of length. This would be a violation.
Okay.
And then they proved that if there was such a hypothetical algorithm, they could use it in a clever way, and suddenly they get a factoring algorithm.
I see. So they need to prove there is a gap first.
No, they need to prove that if